Hello guys, you are welcome back to my YouTube channel. Today I'll be showing you guys how to design a 7-segment octal number decoder using Proteus. The Proteus software is a very popular software that is commercially available and used in most universities across the world. Now, for us to design 7-segment display, we need to first of all decide on which configuration we are going to be using for the design. Here we'll have the common anode configuration. We also have the common cathode configuration. With the common anode configuration, you can see that um, for the word common anode means that all the anodes of the LEDs are connected together. You can see here that all the anodes of for segments A, B to G are all connected together and are linked to the VCC. So that means if you need to activate each segment, all you need to do is to send current towards the cathode because all the anodes are connected together. So the anode is said to be common. If you look at this other configuration here, we have the common cathode. What this means is that all the cathode terminals of the LEDs are connected to ground. They are all connected together and linked to the ground. So that means to activate each element or to light up each element of this 7-segment display, we just need to channel the current towards the anodes of each LED. Okay, so this diagram here clearly explains what happens here in the first two diagrams. Here we can see the common anode. All the anodes are connected together. And here we have the common cathode. All the cathodes are connected together. So you can see here um, we still have all the segments linked. All right, so you can see this terminal here that are not numbered. That's the common terminal. So this is the common terminal, while all of these are the A, B, C, D, E, F, and G. Now moving on. To start with, at the start we said we're going to be looking at octal number. Octal number means counting from 0 to 7. So the first thing we do is to generate the truth table for our design. So here you can see that I've drawn a table for octal number, which is 0 all the way to 7. And here I have a diagram of my 7-segment display to help us understand what's happening here in this truth table. Here, now, first of all, we have decided to use a common anode terminal. What that means is that I will need to, all the anodes are connected together. It means for me to activate each element, I need to send I need to send a zero, which is a zero, to all the elements that I need to be activated. For example, if you look at this display here, if I want to count zero, you see that I need to activate A, B, C, D, E, F. G should not be activated. So G should not be activated. Therefore, I send zeros on all terminals except G. So for G, I send 1. Don't forget, 1 means that element would not be active. So that element will be deactivated. So it will not light up. So in this particular one, element G is not going to light up because I'm using common anode. Same thing applies to 1. For me to activate 1 on the 7-segment display, I'll need to activate only B and C. That means I'll send zeros to only B and C, and all other terminals should be turned off. So again, so you can see here that I have terminal B and C assigned zeros, 0 for B, 0 for C, and assign 1 to the rest of the elements. For me to activate 2, I'll assign 0 to all the elements. Sorry, all the elements that will give me 2, I will assign 0. That means I have element A, B. There is no element C, so I will assign 1 to element C. There's D, E. There's no element F, so I'll assign 1 to element F. Now I go to free. I do the same thing for free. You see that here I will assign 1 to elements E and F. E and F. So that's why I have E and F. On 4, I'll assign 1 to elements. You can see here elements D. There's D here, and there's A at the top. So element there's A there, and there's D. And also you can see there's element E. E is there. So similarly, we complete the truth table. So if you go through all of this, I'm sure you should be able to get this truth table for octal number. Now, the next step is for us to implement this design. Now, you can use Multisim for this implementation. However, I've used Proteus in this video. So what do I do? So this is my design. What I have here is the 3 bits. So this is the 3 bit that is if I go back one step, I mean the D2, D1, D0. Those are the 3 inputs. So that's what I have here. That's the 3 inputs. Okay, D2 at the top, D1, and D0. Okay, so that's what I have there. Now I've implemented this design on paper, which I'm sure this shouldn't be a problem for anybody that is used to electronic design. All you need to do is implement the design. These are the gates: 1, 2, 3, 4, 5, 6, 7, 8. These 8 AND gates here, 3 input AND gates, represent these 8 items: 1, 2, 3, 4, 5, 6, 7, 8. That means 0 to 7. Okay, so 3 inputs. So I use 3 inputs AND gate to represent all those 8 inputs. Now from there, I need to connect where I have one. Wherever I have one, I need to tap that in. So you see in the first one here, I have to activate 0. I only have one at element G. The rest will be 0. So element G is the only one that has 1. So if I go back to the design, you can see here that um, element G, for me to activate 0, I have element G as 1. So I'll just take it. If you're used to electronic design, this shouldn't be a problem. So all you need to do is that I'll go for A. So first of all, let's look at how we activate A. Look at A. For A, I only have one uh, at at um at the second AND gate, that is 001. I have one there, and of course I have one again at 100. This is 1, 2, 3, 4, 5. So I have one at 2 and 5. So we count from the top. We have 7. Don't forget, we have 7 AND gates. Now you can see that for the 7 AND gates, to light up element A, I need everything is 0 except for um, 2, that is first AND gate, second AND gate, 3, 4, 5. Only for 2 and 5. So I'll go back to design. You can see here that I have tapped 2. This is 2 here. This is 2 here. I connect 2 to an AND OR gate, and 5. 1, 2, 3, 4, 5. This is 5. You can also see 5 all the way to that gate. So 2 and 5 come in here to supply my A. So don't forget that the first pin at the top is A. So we have A, B, C, D, E, F, G. So that's the element A. Do the same thing for element B, C, and so on until F. Now, this is our design. Now, let us now go to Proteus and look at the live design. This is just a screenshot. I need to show the live design and let us test out our counter to see if we have succeeded in achieving our design. I'm going to log into Proteus. This is Proteus software. On this software, I have, let me do my test. I'll start with zero. I'll play. This is the play button. If I play, now this program is running now. So if I count 0, 0, 0, that is 0 as expected. The next one is 0, 0, 1. I change this to 1. You can see that now I have 1 active on my display. Now I need to count 2. I'll go back. To count 2, 2 is 0, 1, 0. Now I have 2. Now the next one is free. For me to count free is 0, 1, 1. You can see that I have free there. I need to count 4. To count 4 is 1, 0, 0. So it's 1, 0, 0. That gives me 4. To count 5, 5 is 1, 0, 1. That's 5. To count 6 is going to be 1, 1, 0. So I take that off. I put that 1, 1, 0. That's 6. And to count 7 is going to be 1, 1, 1. 1117. So you can now see that we've been able to test our design, and we're able to count from 0 all the way to 7, which is our octal number. This theory can be extended to counting 0 to 9, which is decimal numbers, or the hexadecimal numbers can also be done in the same format. Now, I'm going to have another video where I will implement this on a breadboard, just to show us how these circuits can be taken into the lab, the experiment stage, and where we can now use ICs to bring this to life. I hope you've learned something today. I'm sure you can try your hands on any design of your choice. Probably do a decimal number design. Please, at this point, I would like to remind us, if you want to have a lot of this content, please subscribe to this channel, and you will be sure to get lots of information that will help you in your studies. Thank you for listening, and I hope to see you sometime in the near future. Bye.